Hey guys, welcome back. We got day 17, factors that affect acid strength, and we're also going to talk about Lewis acids and bases today in this video. So first of all, acid-base strength. When we talk about acid-base strength, we're talking really, when we say strength, we're talking about the size of K, whether it's Ka or Kb, which we're talking about the size of it. So when we talk about acid strength, binary acids first. What are binary acids? This is where H is bonded to A, HA. No oxygen. Two factors affect strength. The first factor will be bond polarity. And what does it have to do is increased bond polarity equals more acidic. Increased bond polarity equals more acidic. Examples. Let's talk examples. So when we talk about examples, if I have CH4, NH3, H2O, HF. And we talk about polarity. Remember the top five? Electronegative. We had fluorine, oxygen, chlorine, nitrogen, bromine. Now, if we remember, bond polarity has to do with delta En, right? The electronegativity difference between the two bonded atoms. And anything from 0.5 to 1.9 is polar. We're still going to do the top five, if it's polar or not. That hasn't changed. But what I want to point out is that the electronegativity of carbon is 2.5, nitrogen 3.0, 3.5 for oxygen, and 4.0 for fluorine. And we look at Ka, we have not acidic, still not acidic, 1 times 10 to the negative 14, and 6.8 times 10 to the negative 4. So as the bond polarity increases, the electrons are not being shared as much, so H is more likely to leave. That kind of makes sense. Number two is bond strength. So the strength of H bonded to A. The strength of this bond right here, that bond strength. So the weaker the bond, the stronger the acid. That kind of makes sense as well. The weaker the bond, the stronger the acid, because it's more likely to break, more likely to dissociate. And so some examples, HF, HCl, HBr, HI. Hydrofluoric acid, hydrochloric, hydrobromic, hydroiodic. Bond strength. When we talk about bond strength here, HF 565 kilojoules per mole. HCl 431 kilojoules per mole. HBr 364 kilojoules per mole. And HI 298 kilojoules per mole. And we're going to just say that we have the weakest, the strongest. In fact, in Chem 1, HF is the only one with the constant. All the other ones we just consider strong. And we're going to keep it that way. So those are the two factors that talk about acid-base strength, or acid strength, for binary acids. There's a second class of acid, and these are oxyacids. And you have the H. It's bonded to oxygen. You got oxygen in there and a central atom. Now they're usually written as HYO, and however many oxygens there are, like nitric acid or sulfuric acid. But they're always bonded, H bonded to the O. And again, two factors affect acid strength. Or I could say that as two factors affect the size of Ka. The first one is the electronegativity of the central atom Y. I'm going to put that in parentheses because in this case, oxygen is a central atom, so Y is not a central atom. But a lot of times we're talking about the non-oxygen atom. And when there's more than one oxygen, it becomes central. So, for example, as the electronegativity of Y increases, acid strength increases. K becomes larger. For example, HOI, HOBr, HOCl. Now, a lot of times we'll write them as HIO, HBRO, and HClO. Either way we write them. The electronegativity of iodine is 2.5. Of bromine, 2.8. Chlorine, 3.0. Ka for HOI, or HIO, hyperiodate acid, will be 2.3 times 10 to the negative 11. We'll go up to bromar, it's 2.0 times 10 to the negative 9. That's 100 times bigger. And then 2.9 times 10 to the negative 8, 10 times bigger. So as the electronegativity increases, it's more acidic. The second factor would be the number of oxygens bonded to Y. And with this, as the number of oxygens increase, acid strength, or K, increases. Well, examples. I got HClO, HClO2, HClO3, HClO4. Hypochlorous acid all the way to perchloric acid. The oxidation state of chlorine. So my ox state of chlorine, +1, +3, +5, +7. Ka, again, 2.9 times 10 to the minus 8. If we go to +3, we get to 1.1 times 10 to the negative 2. That's a million times bigger. Then we get somewhere around 1. And then we have perchloric acid, which we're just going to say large. Large Ka. Probably around 10 to the 9th, just so you know. So that's the factors that affect strength. Next topic we're going to talk about is another way to look at acids. We're talking about Lewis acids and bases. Now, if you remember Lewis and the Lewis structures, same guy. Lewis talks about, electron pairs and sharing electron pairs and, how do you arrange the atoms with the electron pairs. Well, Lewis is going to look at electron pairs in terms of acids and bases. So we've been looking at H plus or hydronium, and right. So there's three definitions. Arrhenius, you produce H plus or H3O plus if you're an acid. You produce hydroxide if you're a base. Then Bronsted-Lowry, which is probably the most important for aqueous system, is proton donor, proton acceptor. You donate the proton, you are an acid. You accept the proton, you are the base. Well, there's Lewis acids and Lewis bases. Lewis acid now is an electron pair acceptor. And the base would be the electron pair donor. Electron pair donor. So a couple of things with this. One little note that CNOF cannot exceed 8 valence electrons, right? They're not going to violate the octet rule that way. They can't exceed it. So if we go through H plus or H3O plus versus OH minus. So H3O plus is an acid at all definitions. And hydroxide is a base under all definitions. So hydronium is an acid in Arrhenius, Bronsted-Lowry, and Lewis. Hydroxide is a base in Arrhenius, Bronsted-Lowry, and Lewis. They don't change. So you see hydronium, it's acid. You see hydroxide, it's base. That does not change. We're just looking at it from the electrons now instead of the protons. Note, water is only a Lewis what? So if I look at HOH bond, water has 8 electrons, or oxygen has 8 valence electrons. Water has 8 valence electrons. Oxygen has 8 valence electrons, and it can't gain any more. So water cannot accept a lone pair. Hydrogen is not going to accept a lone pair. It has its duet. So if water, H or the O, cannot accept a lone pair, they cannot be a Lewis acid. Water, however, can donate one of the lone pairs to something else, make a coordinate covalent bond, so to speak. So water is only a Lewis base. Water is not an acid. Now, in Bronsted-Lowry, water can be either. Water can be an acid or a base because it can donate a proton or it can accept a proton. But in the Lewis definitions, water is only a Lewis base. Another note, all metal cations are Lewis acids. They can accept an electron pair. So let's go really simple. H plus NH3 going to NH4 plus. Well, H plus is still going to be an acid. It has, in fact, H plus cannot be a base. It cannot donate an electron pair because it has no electrons to donate. We don't have any electrons to donate, so I can't donate any. All right, this is why I don't give millions of dollars a year to cancer research or Parkinson's research or any other medical research because I don't have millions of dollars. It's not because I don't care about it. It's I don't have millions of dollars. H plus has no electrons. Now, it doesn't think like a human, but it cannot donate electrons if it doesn't have electrons to donate. H plus can definitely accept electrons. Nitrogen has that lone pair. Nitrogen is the base. This here, NH4 plus, we actually call an adduct. An adduct. And that is the product of a Lewis acid base reaction. Another one. NH3 plus BF3 going to BF3NH3. NH3 would be what? Well, it's still a base. It still has the lone pair. BF3 would be the acid. And then our adduct. So how do I know that? Well, if I need to, N, H, 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 B, F, F, F. I can draw them. Now, fluorine is not going to violate that TET rule. We're not going to add anything to the fluorine. Boron only has 6 electrons. So what's going to happen is that this lone pair right here is going to go right to the boron. Oh, I erased. There we go. That's what's going to happen. Exactly what's going to happen. Another one. SbF5 plus fluoride going to SbF6. What do we got? Well, SbF5 would be Lewis acid. Fluoride would be the base. And how do I know that again? How do we know that? Well, antimony pentafluoride. Antimony has 5 valence electrons. Fluorine has 7. So 7 times 5 is 35, plus 5 would be 40, or 8 times 5 is 40. Antimony is in the middle, because fluorine is not. And we can draw that out. 2, 4, 6, 8, 10, and then we got 12, 14, 16. You remember doing this. Fluoride, F minus. Well, actually, the minus is outside the brackets. And we can use different colors for fluorine. Fluorine, F minus, cannot accept any electrons because fluorine has 8. However, fluorine can donate electrons to antimony. And that'll work because antimony can violate the additive rule. It already is doing it now. So that's the Lewis acid, Lewis base. Let's do a couple examples and we'll go from there. So day 17, 119, I want to know the stronger acid and why. So for A, what one is stronger? It's a great question. And I'm going to say sulfuric acid is stronger. Well, we know why. Well, he told me to memorize it. It's one of my 7 strong acids. And that's good, but that's not why. That's what I told you to do. Why is because there's more oxygen on sulfur. So sulfur in this case would be what? Plus 6 versus plus 4, I believe. Yeah, because minus 2, minus 8, plus 6. Yeah. So sulfur is higher oxidation state. More oxygen on sulfur. That's why. Same thing with B. More oxygen on chlorine. What about C? Well, we go back in our notes here. If we go back to the top page, I can look at I wrote down Ka values, but chlorine will be, chlorine would be more acidic because Cl is more electronegative. And finally, you have trichloroacetic acid versus acetic acid. Well, chlorine is more electronegative, and so it's going to have a higher Ka value. That's it. That's all we got. 123. Classify each species as a Lewis acid or base. Iron 3 plus. You got transition metal. Transition metal is very electron poor, so it wants electrons. I'm not going to donate electrons. It wants electrons. So therefore, it's going to be an electron pair acceptor. And an electron pair acceptor would be an acid. B here, BH3. Well, BH3 does not have much electrons to donate. It's also going to be a Lewis acid. NH3, ammonia is a weak base. It's still a weak base. It's always going to be a weak base. Ammonium is an acid. Fluoride, F minus, has an electron pair to donate. Base. So can I donate a lone pair, or do I have a parking spot for a lone pair? So X, and if I have electrons, if I have an opening here, there's 6 electrons, I'm an acid. I can be an acid. X, if I have all full, I'm probably going to be a base. So now let's look at this one. BeCl2. Is that an acid or base? Well, chlorine's full. Be has 2 bonds. It can probably accept another lone pair. I bet you that's going to be an acid, because we have Cl, Be, Cl. That's stable, but we can actually absorb more electrons in there. And there's orbitals to do that. So if you look at beryllium's electron configuration, it's 1s2, 2s2. The 2px, 2py, and 2pz are still there, and they're empty. They can definitely have electron density in them. Hydroxide's always going to be a base. BOH3. Well, I just said hydroxide's always going to be a base, but is that hydroxide? I don't think that's hydroxide, because B and O will make a covalent compound, won't they? It's polar, but polar bond, not a polar molecule, polar bond. But boron can accept electron density. You can accept electron density here, so this is going to be an acid. Cyanide, most of the time, if you're negative, you're going to be a base. Cn minus, especially these ones. Both of them can do it, both pairs, but mostly the C can attach. So cyanide is a major base. So you just got to look at, is there room to actually add another bond, or do I take some of the electrons I have and make a new bond with the electrons I have? If I make the bond with the electrons I have, I'm an electron pair donor, I'm a base. If I can take some electrons, I have a spot, I'm an electron pair acceptor, I'm an acid. 125 and 126. Acid. So acid will be green, base will be blue. Acid, base. So, metals. Metals are going to be what? Metals are always acids, aren't they? Transition metal, positive, acid. And water can be a base. Zinc 2 plus, acid. Water can be, or ammonia is always a base. Nitrogen. I have nitrogen that's not positive. Nitrogen is still a base. That's a base. Which means boron trifluoride, definitely going to be an acid. Same thing with 126. Silver is going to be an acid. Ammonia is going to be a base. Aluminum bromide and ammonia. Ammonia is still a base. Fluoride F- is a base. That means the rest of them, the other ones are acids. So hopefully that makes sense how you go through without drawing them out. Just knowing if I'm negative, I'm probably going to be electron pair donor. I'm going to be a base. If I'm positive, I'm electron pair acceptor. Going to be an acid. Nitrogen, neutral nitrogen, ammonia, and this is like a derivative of ammonia at CH3,3N, trimethylamine, always going to be a base. So that concludes acids and bases. So that concludes day 17. Hope everything went well. Hope you enjoyed it. Take care, guys. We'll see you next time.